So let me briefly introduce Felix Otto. He got his PhD in 1993 from the University of Bonn, and then did postdocs at the current institute of NYU and then at Carnegie Mellon. From there, he moved to UC Santa Barbara as a professor. And then he came back to Europe to become a professor at the University of Bonn until 2010. And from there, he moved to the Max Planck Institute for the Mathematics in the Sciences, where he's a director. And we're looking forward to a Blackboard talk now. Thank you.
Thank you very much. Thank you for the invitation. It's an honor to be here at this occasion, and a pleasure to be at the Schrödinger Institute. So while I know Martin since a number of decades by now, I would say, I really got into what he was doing, regularity structures, thanks to Hendrik. I got kind of a very efficient introduction to that set of work. And while by training, I would say more of an applied PDE person or calculus variations person even, it became a topic where together with a number of collaborators, I think in the last number of years, I put most of my effort in, because it's a fascinating subject for somebody even outside of mathematical physics or probability theory, just from a pure PDE perspective. And what I would like to do today, so that's not going to be very new for Martin, but perhaps for some people in the audience, is in a certain sense to present my interpretation or our interpretation of the tools which Martin has introduced. And I want to do that in case of a very specific example, and using a little bit the language which Hendrik already kindly introduced. So let's think of kind of a parabolic partial differential equation, and in order to make it very simple and to stress the fact that it could as well be an elliptic partial differential equation, I will just look at one space dimension and denote this by the kind of the space-like derivative, and x2, or this symbol will correspond to the time-like derivative. And we're going to be interested in an equation that's driven by noise. I'm going to use the same notation as Hendrik. Think of white noise, or of a noise more generally, which is such that your solution is Hölder continuous with a positive Hölder exponent alpha. Think of alpha as being 1/2. That would be, for instance, the case. So that's clearly the case if you just had this equation. If your noise typically would have realizations which are distributional of the order of alpha -2. And let's think of white noise. So the case of white noise, this is kind of this numerology which Hendrik already introduced. The regularity of white noise on a Hölder scale, or on any kind of also Bezoff scale if you want, essentially is minus the effective dimension over 2. And in this problem, the effective dimension, as PDE people know and physicists certainly also know, is 1 + 1, because there's just one space dimension. But then the time dimension counts twice. So this would be -3/2. In case of Hendrik, it was -5/2, because he was working in 3 space dimensions. Here it's just one simple space dimension, so it's -3/2. So that would be equal to alpha -2 for alpha is equal to 1/2. Yes. So the white noise case corresponds to alpha equal to 1/2, but it's helpful to unfold this a little bit and think of a more general alpha, but it will always be positive. Okay, so far there would be no problem at all. It would be a boring linear equation. Of course, the solution has a limited regularity, but there would be no interest. Now you add a nonlinearity, and I could add a KPZ type of nonlinearity as Hendrik introduced, but I will focus on another type of nonlinearity which we took a liking in, because it's kind of a mild form of a quasi-linear nonlinearity. So it's kind of slightly beyond the semilinear case, but that's not a big deal. And I want to make the point that this is a problematic term. Why is that a problematic term? Because if your nonlinearity A is smooth, and I will always assume this, so think of some constitutive equation, some constitutive law which defines this nonlinear medium. This, of course, will be also a C alpha function. And taking two spatial derivatives of the solution will reduce the regularity by 2. So this term, in fact, has the same regularity as the right-hand side, so alpha minus 2. And then it's this basic observation that you can form in the classical way the product between a function and a distribution only if the regularity of the function is better than the irregularity of the distribution. Otherwise, things get interesting. So this would be singular if the sum of the two regularities is negative, and that's of course equal when alpha is equal to 1/2. Alpha is less than 1, which means the case of alpha equal to 1/2 is already the singular case. There is something interesting in one space dimension if you push it by white noise. And so, as Hendrik has said, kind of this type of equation therefore calls out for what's called a renormalization. So let me try to explain that in kind of very lay terms. So the idea is that you want to fuss with the equation. You want to change the problem, but you want to change it in a certain sense in a minimalistic way. So let me kind of be bold and add an additional term here, h of u, and tell you that that the goal is, so the goal of renormalization is the following. So let's regularize the problem by some kind of ultraviolet cutoff of, for instance, the noise. So by a convolution. So you replace psi by psi epsilon. And now you want to choose a counter term. So that's the language. Counter term h, which is a function of h of epsilon, and which clearly, because one is in a singular situation, in a certain sense diverges as epsilon goes to 0, so that you achieve two goals, two kind of conflicting goals. The first goal is that you want the solution manifold of the renormalized problem. So let me denote that by U. I'm using American spelling. Renormalized manifold to stay controlled as epsilon goes to 0. And the other goal is you want to kind of preserve as many symmetries of the solution manifold of the original equation as possible. And one symmetry, which is perhaps on the one hand quite obvious, but on the other hand perhaps not that obvious, is the following. So clearly this equation we're started with, so without the renormalization term, has one basic property, namely if the couple of a function u and a nonlinearity A solves is a solution, then I can shift the solution by a constant, and I can shift the nonlinearity by the same constant, and I still get a solution. So in a certain sense, it doesn't matter where I put my origin into U space. And therefore, a consequence is that whatever renormalization you do, it should preserve that symmetry. And that has the following consequence, that this function h, which depends on epsilon, but now I'm going to suppress this, which is some functional of the nonlinearity A and a local function of the solution u, or the function u, so it just depends on the value u in one point, so think about this as being just a real number. That should be the same as shifting the nonlinearity and shifting the argument, right? That's obviously a very natural prerequisite. And that has the following consequence, that the form of the counter term is restricted by saying that it has to be just given by functional on the nonlinearities, and then you recover this function by shifting the nonlinearities. So there exists a functional C on the space of constitutive laws of A's such that this holds. So that's kind of a very simple-minded, but in fact, extremely important constraint on the structure of the counter term. So before I kind of rephrase that in a somewhat more algebraic way in the spirit of regularity structures or a term-by-term treatment, let's do the same thing for the solution. Let's try to find kind of parametrization or make an ansatz for parametrization of the solution or solution manifold. And let's at first think of the special case when the nonlinearity is not present. Then by this property, we know that the counter term in fact is constant, which means that in this special case, the solution manifold is affine, right? We're just solving, we're just dealing with an affine manifold, and that has a kind of a canonical parametrization once one fixes a base point. After fixing the base point, so point, I mean something in time space. And I'm using the same language as Hendrik, because I'm gearing up towards, or I want to get you towards Martin's notion of a centered model. So after fixing a base point, there is a way of a canonical way of parametrizing this this affine manifold, because there is a canonical solution of the linear equation, provided you impose its value at one point, so you set it equal at the point x. And zero, why I put a zero here will become apparent in a second. And therefore you can write a general solution, u, as this, or let's look at the increment, u minus ux, as this specific solution, plus kind of a general solution of the homogeneous equation. And I'm now simplifying a little bit and think about this not as general caloric polynomial, but just any polynomial. Which vanishes at the base point. So if you're interested, and let's focus on this, just on solving the equation up to polynomials, which is okay because the right-hand side is rough, that would give a parametrization of the solution manifold in the easy case when there is no nonlinearity. And now the ansatz is that this type of, and if you want, in the spirit of Cauchy-Kovalevskaya, extends into the nonlinear setting, so that you can find a function which depends on the base point, a functional which depends on the base point, which takes in the shifted nonlinearity, shifted by the value of the function at u, and a shifted polynomial. So that would be kind of motivated by this here, a halfway reasonable ansatz of how you would hope to parameterize the entire solution manifold, also in the nonlinear case. Now let me look for a second on my slides, how I wanted to continue. Yes. Okay, so now what I want to explain now is, so this is in a certain sense just a very general form of how you think of parameterizing your counter term and parameterizing your solution manifold. And now I would like, in the spirit of regularity structures, in a certain sense, to algebraize this, which is perhaps a too fancy word for this audience. So, I mean, in a certain sense, doing a term by term ansatz of this. So what do I mean by this? I mean that I want to put coordinates on A space, and natural coordinates on A space, of course, are given by the derivatives of the nonlinearity A, the jet of the nonlinearity A in, let's say, the value of u equal to 0. Then I'm looking at monomials. Oops. So I look at z to the power beta, and beta is a multi-index. So what I'm thinking of is taking the product over the coordinates functions to the power beta k. So that's kind of standard notation, just with the difference that here you have kind of an infinite number of these coordinates. And then you make the ansatz that this functional, which you're looking for, is a formal power series, which means oops, you have this form here, and here you're summing over multi-indices. So in algebra notation, you would say that's a formal power series in these variables. And so why do we do that? Well, because at least if A were analytic, we can recover the full nonlinearity by Taylor, which would amount to this identity. But more interestingly, this counter term here would be recovered in the following way. It would be, can be written as an exponential type formula, where here we have u to the power L, and here we have d0, which I'm going to explain in a second, applied to C times A. And this d0 is the derivation on this, this algebra. Which generates the shift. So in fact, I can write it down. It's the sum over k plus 1, zk plus 1, dzk. So so this is now kind of an algebraic way of implementing this. And now we do exactly the same thing for this ansatz here. So that means we also need coordinates on P space. So that's not very interesting. We just take the same, we just make the same approach. We take the space-time derivative of the polynomial, let's say in the origin, which of course is pretty arbitrary. So n now is a multi-index, a two-dimensional space-time multi-index, but I rule out n equal to 0, because these polynomials always vanish in the origin, because the polynomial which I put here has to vanish in the point x by this normalization. And so those are coordinates on P space. So I now have monomials which are slightly more complicated. So there is a first part which is related to the first set of variables, and there is a second part which is related to the second set of variables, beta n. So beta now is a multi-index in the k and the n. And let me see what the formula which I want to write down now. And then, right. And then we want to make the ansatz beta x of AP. So this object we're interested in, we again write it as a formal power series now in this extended set of multi-indices. So px beta a p, no, px beta z beta a p. So same algebraic ansatz. And what it really means, if you plug this into this formula, and you use the definition of the multi-indices, this implies that we try to write increments of a general solution as this formal sum over these coefficients, which are random space-time functions, times something which depends just on the one hand on the nonlinearity. So here is 1 over k factorial dka duk, but at the point u of x to the power beta k, that's what comes from here. And then the product over all n not equal to 0, 1 over n factorial del n p del xn at x now to the power beta of n. And this is something which is not completely unusual. That's something which can be seen as a generalization of a B series or Butcher series. Okay, so that's the ansatz we make, and this is just kind of an algebraic way of rephrasing the problem. And the nice thing is now that the equation, so the original equation, which is up there, let me put it up once more. Plus, let me change the order, minus the counter term, plus xi. This one translates into a hierarchy of linear problems which are indexed by beta, but which can nicely be written in compact form using the algebra structure. So I can write this as the linear operator applied to pi x. So the object which the formal power series with these coefficients is equal to 3 terms. So there is a sum over k, which involves the coordinate functions at k, which involves the kth power of pi x, which makes sense in this algebra. So this is an identity in this algebra of formal power series, times the second derivative. So clearly, let me use colors. Clearly this term corresponds to this term. That's just Taylor using this identity. And then there is the counter term, which is, again, the sum over L. All these sums are effectively finite. 1 over L factorial, pi xl, d0 to the pi L applied to C. So that's So here we're looking, that's the what corresponds to this term. Let me take out the minus sign. And that has to do with this formula. And then there is the right-hand side, which, if I write it in this form, is multiplied with the unit element in this algebra. ZK, ZN. And let me introduce the notation pi x minus for this object. So that's in a certain sense a rephrasing of the attempt to kind of construct or write down the entire solution manifold by the term-by-term way. And at least as long as you have the regularization, that is perfectly sound. So as long as you put the epsilon here, and then of course you acquire an epsilon there. But now the interesting question comes up, because in the end we want to, in a certain sense, pass to the limit, which means that this way of writing the right-hand side is not a very suitable way, because it contains these divergent constants. So we have to find a better way of writing this right-hand side. Oh, by the way, so I said it already in words earlier. So this here, and I'm using exactly the same notation, is the what's called the centered model in regularity structures. Okay, so the challenge is to find kind of a more robust definition of the right-hand side pi x minus. So task. Oops, sorry. I don't want to break the furniture here. So find a more robust of the relationship or the map, which goes from pi x to pi x minus, and which allows us to, which in a certain sense avoids the C epsilon which diverge, and allows us to pass to the limit epsilon going to 0. Why is that beneficial in several ways? So one way, so how much time do I have? Okay, 20:45. So we now need to raise. So one way why kind of doing this is beneficial, besides that this is what we really wanted to do in the first place, is that there is a scaling that emerges only in the limit, because only in the limit we can really work, for instance, with space-time white noise or any other scale invariant, let's say Gaussian random field, because any type of ultraviolet regularization would break that scaling. So so let me, before I tell you what the kind of main idea is, to avoid rewriting kind of this relationship between the solution and the right-hand side, let me tell you what the benefits of it are. So the advantage of this is that we can allow for, we can now consider, so let's say consider the parabolic rescaling So Sx rescales the space-like variable and the time-like variable in the usual parabolic way. So let's consider this. And if we remove the regularization, it makes sense to consider a noise that's invariant. I have to put there as alpha minus 2 under this rescaling in law. So for instance, white noise would be invariant under this rescaling with this exponent being minus 3/2. And then it's clear that also the solution manifold should inherit this rescaling in law. Inherits the scale invariance in law. And therefore, it's reasonable to also construct our objects, our, if you want, charts, in a way that they preserve the scale invariance in law, and that would amount to this type of relationship, x beta, where this is kind of a number which can be associated to multi-index, in which in regularity structures is called the homogeneity. And here, since we have functions, it's always non-negative. So, in passing to the limit, we would hope that we can preserve, or we can get this, this independence in law. And what's the nice thing about this? The nice thing about this is that together with invariance with respect to translation, if we would look at a component, x beta evaluated at y, we would know that its pth moments, let me take kind of a form of a stochastic LP norm, exactly scales in the following way. There is a constant which only depends on the multi-index beta, and p times the parabolic distance of y to x to the power of the homogeneity. So that's a nice property, because by a PD ingredient, which is called Liouville principle, this tells us that for given right-hand side pi x minus, there exists at most one pi x beta with this property, with this estimate, that solves the linear equation. So, so this equation, if I think of this as being externally driven, this is, so there is a caveat. This only holds if the homogeneity is not an integer, which in fact forces us to be on the safe side to assume that alpha is not rational, which unfortunately rules out the case of alpha equal to 1/2. And perhaps I come back to this at the very end. But that's something which creeps in here for PDE thesis, for PDE reasons. So PDE, I mean, the Liouville principle tells you that caloric functions which have a certain growth at infinity, which is contained here, have to be caloric polynomials. But at the same time, this gives you a certain order of vanishing near the base point x, which tells you that the polynomial has to vanish, but that only works if this exponent is not an integer. Okay, so that's the beneficial part of passing to the limit. So what's the idea of doing this? The idea is to take derivatives with respect to the noise. So to introduce, to use Malliavin calculus. So that's the last thing which I want to, thank you, which I want to explain. Why this is a good idea and what it involves, and which also connects to the second ingredient of regularity structures, which is the base point transformation. So that's so the idea is, or the Ansatz is to take derivatives, to take a derivative with respect to the noise psi, and for the experts, that's what's known as Malliavin derivative, which is a little bit technical, but I'm not going to worry about this here. And why is that a good idea if you want to get rid of the constant C, because the constant C are deterministic? So let's introduce some notation. Delta denotes the directional derivative with respect to an infinitesimal perturbation of noise. So for the experts, that would be an element, if we were in the Gaussian case, of the Cameron-Martin space. So the delta for me is an operator which takes a directional derivative of the model or any other object if I vary the noise. So it's like in applied math when you linearize a problem. And so what's the big advantage? Because by postulation, so by the assumption that C is deterministic, perhaps I didn't stress this enough, but of course that's part of the basic assumption. If we take the Malliavin derivative of C, it vanishes. So the first attempt would be to just apply the Malliavin derivative to this formula and hope that the C's go away. That's clearly not the case because the C doesn't appear in an isolated way. It's multiplied with this prefactor, and that's really part of the problem because it comes from kind of the U shift. So this at first works just in a very impoverished way. Namely, if we evaluate at the base point, because at the base point, this relation here collapses a lot because these objects all vanish at the base point, and we're just left with the k equal to 0 term and with the L equal to 0 term. So at the base point, we have this relation here, minus C plus psi times 1. And therefore, if we take the directional Malliavin derivative or noise derivative of this identity, indeed, the C drops out. So that's good. But clearly, this is very impoverished, right? And here I should put a minus, and here also minus. So in a certain sense, we need to free ourselves. If we want to draw information, we need to free ourselves from having the active variable equal to the base point. And that's exactly where Martin's change of base point transformation comes in. So need change of base point transformation, which is a kind of a change of coordinates, which is not surprising that it should exist because remember that general solution we can write both with respect to the base point x. So let me kind of remind you of this formula here, z to the power beta a plus u of x for some polynomial p at x, but we can also write it with respect to the base point y. And clearly that should give us some kind of relation Okay, so here it doesn't fit. Some kind of relation between these coefficients and these coefficients. And let me see what I'm going to raise now. Oops, we can. Probably I want to keep this, and I'm going to raise that. So again, I'm going to use Martin's notation for this, because it's exactly what he introduced. So what we get is that there exists an object gamma, actually I need it the other way around, yx, which is an algebra endomorphism of this algebra of formal power series in these two sets of variables, such that pi y can be written as gamma yx applied to pi x plus a constant term, which is pi y at x. And in view of this very specific structure, we have an additional information on this element, namely on this sub algebra. It is given by essentially such a formula. So it's equal to 1 over L P x y to the power L P0 to the power L. And because it's an algebra, it also does the same job on the right-hand side, even without this constant term. And in fact, it's also identity minus this transformation is strictly triangular. With respect to the homogeneity. So those are properties which in a certain sense can be inferred from this representation, but which are at the same time parts of the axioms of regularity structures. And now the idea is, in a certain sense, to hit this identity here with the space point transformation in order to get rid, in order to produce a y there, in order to get rid of this impoverished situation. So, and indeed that works, but as I will explain, it will not yet quite do the job. So what we get is, by Leibniz rule, for the Malliavin derivative, we get that pi y minus the Malliavin derivative of this change of basis formula, pi x minus both at x, can be written as the sum over all k, zk, pi x k y, and then a very similar expression, but now without the minus, pi y minus delta pi y x minus delta gamma yx applied to pi x at the point x. And now this is in a certain sense a nice identity because it mimics the relationship which we have between pi x and pi x minus, however, on the level of the Malliavin derivative, but without the divergent constant c. And yeah, I forgot this term. And but it doesn't So there's the last thing which I have to tell you. So it doesn't quite work. So what's the reason why it doesn't quite work? So and that has to do with analysis. So far, everything was essentially what I told you were essentially algebraic observations. So I have to bring in a bit of analysis. So what's the benefit of, what's the analytical benefit of taking a Malliavin derivative? So you're replacing an instance of the noise, which is a pretty rough object, by an instance of the Cameron-Martin space, which is a much less rough object. And that's a gain in regularity of d over 2. So 3/2 in our case. That's cheating a bit because here we're measuring in with respect to the Hölder scale, here we're measuring with respect to an L2 scale, but that's, let's say, for the moment, a detail. So we gain this regularity, and that's good because therefore we expect that this d pi gamma has regularity, at least in some vague sense, of alpha, which would be the regularity without the Malliavin derivative, plus d over 2. And that's certainly regularity which is larger than 1. In fact, it's close to, for white noise, it would be exactly close to 2, but in general, it's even larger than, yeah, let me stress here that it's larger than 1. And then, if you think about it, what you find here is a little bit like a Taylor remainder. So you look at the Malliavin derivative, so Taylor remainder of the Malliavin derivative, the directional Malliavin derivative of the model in the point y at the base point x, because you look at the increment and then you subtract something more. So you would like to interpret this as a Taylor remainder, but it's not. At least it's not a Taylor remainder which captures this regularity because of the strict triangularity of this object. It often does not contain the linear term. So that's the last thing which I want to tell. And then I'm going to stop. So the problem is that because of strict triangularity, of this Malliavin derivative of the change of base, often, so for many components, the term x1 is missing. But this one we would need in order to kind of control this quantity here. And the idea is now to augment this property, so replace it by something, if you want a matrix that's more populated, while retaining the algebraic properties. And the two important algebraic properties is that this new object still should be something which, roughly speaking, is in the tangent space to what's called the structure group, or let's say the automorphism group, the algebra maps of our algebra in the point gamma yx. That in a certain sense amounts, that's a fancy way of expressing some kind of Leibniz rule. And we want to preserve this property in the sense that E gamma xy is equal to del gamma xy on r zk. And with these two properties, one can, just by completely algebraic manipulation, show that you can replace the del by the d, and that gives you enough flexibility to really treat this as a Taylor remainder and to make that small. So that's the idea. And in the end, what one gets is exactly what should be gotten by regularity structures. So that's a theorem together with a former PhD student, Pablo Linares, with the current PhD student, Markus Tempelmeier, and a former postdoc, Carlos Tsatsoulis, where we show that indeed, if your noise ensemble satisfies a spectral gap condition, the right type of spectral gap condition, which allows to go from the Malliavin derivative to the original object, we can construct the model in kind of by unique algorithm with the right estimates. And in fact, that's something which Markus Tempelmeier is working out. This limiting model is also unique. And the uniqueness comes from this type of representation, which passes to the limit with high-rise estimates. But the caveat is we need this because of purely analytical reasons. We need that alpha is not a rational number. And that, of course, is problematic because, in fact, we want to treat alpha equal to 1/2 because that's the most natural case. That's white noise. But then it's clear that logarithms will have to appear, and something which we didn't even dare yet touching, namely the renormalization group in the sense of regularity structures, would have to come in, because in that moment, this uniqueness gets lost. So then there will be a choice. But in many situations, in fact, there is this completely canonical way of passing to the limit and making sense of a limit model using the Malliavin derivative. Okay, so I think I'm anyway over time.